Here's an example of using integrals to find the area of a region when a curve is described using parametric equations. Let's find the area enclosed by the loop of the curve x equals 1 minus t squared and y equals t minus t cubed. To start, let's look at a graph of this curve. Here's a rough sketch of the graph of this curve. If you think about what the behavior is of these two functions, the function for x and the function for y that make up this curve, you can kind of convince yourself that this graph is reasonable. The function for x is x equals 1 minus t squared. Now, if you graph that in the xt plane, you would have a parabola. What it really means, though, is that this is a function in which x starts off very low, goes up to a certain maximum value, and then goes back down again because you have a parabola opening in the negative x direction. And sure enough, in our curve, x is starting off very low over here. This is a low x value, going along, getting higher and higher and higher, and approaching some maximum value. Actually, the x goes to the maximum value of 1, and then our x goes back down again. So if you look at what happens left and right, this loop is doing exactly what we expect x to do here. Meanwhile, what is y doing? Y equals t minus t cubed. If you were to graph that real quickly on the ty axis, here's t, here's y, you have a cubic equation, a cubic polynomial that looks about like this. It's going to go down, up, and then back down again. So what's happening to y? Y starts off very large, very high, up here somewhere, goes down, 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 down to some value below 0, goes back up to some value above 0, and goes back down to minus infinity. So while x is moving from left to right and then back to left again, our y starts off very high, goes down to some low value, back up again, and then back down again. That's why we're getting a loop in this graph. So the region we want to find the area of is this region in here. This entire region of this loop, the region enclosed by this loop. But to find that area, we'll need to be rather clever. So first of all, we can convince ourselves this is actually a symmetrical region here. This graph is symmetrical. The fact is, because our x function is an even function, 1 minus t squared, it means that x is doing exactly the same thing forward and then doing that same thing in reverse again. Meanwhile, our y function is an odd function, which means that for negative values of y, we get the exact opposite of what we get for positive values of y. If you were to eliminate the parameter and get an equation in terms of x and y, you would find that that graph is in fact symmetrical across the y-axis. So what that tells us is we can actually find the area of just the top region here and double it, and it will be the area that we need. So we want to find this area and double it. So our next question is, what are the values of our parameter when that happens? Well, over here at this rightmost point here, our x is equal to 1. And over here at this leftmost point, our x is equal to 0. And at both points, our y is equal to 0. But let's try and take one of our equations and solve for when x equals 1. Actually, we'll take the x equation, solve for when x equals 1, and that'll help us figure out what our parameters, what t is when x is 1. So, if x equals 1, that means that 1 equals 1 minus t squared. And of course, we can subtract 1 from both sides, and we get that 0 equals negative t squared. So t is, of course, equal to 0. So what that tells us is, at that point, the rightmost point, our t is equal to 0. Let me mark that. At this point here, our t is equal to 0. Now, what about this other point here at the top? Well, let's work that out. That's when our x is equal to 0. So, if x equals 0, then we have 0 equals 1 minus t squared. And we can solve this by factoring. In fact, you should solve it by factoring. You should not solve it by adding t squared to both sides, because that's going to lead you down a path that will cause you to miss one of the solutions here. Let's factor this. 0 therefore equals 1 minus t times 1 plus t. And that means that 1 minus t equals 0, which means t equals 1, or that 1 plus t equals 0, which means that t equals negative 1. So over at this point here, the point at the origin, t can equal plus or minus 1. Which value of t do we want to give us the boundaries of the region we actually are interested in? Well, our y value, when t is very low, when t is a negative number, our y value is actually positive, because t minus t cubed is going to be negative, but negative t cubed being positive, and that's going to take over. So we're going to start off up here on the top, and we're going to move down, 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 and around the curve like this, and end up going back down again. So our y starts off positive and ends up being negative, and that tells us what direction we follow this curve. So if we were to use t equals negative 1 as the boundary of our point here, and look at the values of t between negative 1 and 0, we'd be following this bottom half of the curve here. I don't really want to follow that part of the curve because the y values there are negative, and that means that when I set up an integral for the area, I'm going to get a negative answer that's just kind of, I don't really want that. So let's avoid that. Instead, if we go from t equals 0 up to t equals 1, we'll be following this part of the curve that we want. So let's use t equals 1 as our ending point. So I'll rewrite this value here and say that t equals 1. There are two t values where the curve goes through the origin, but the t value of 1 is the value we actually want. When t goes from 0 to 1, we trace out the top part of that loop, and the area underneath that is the area that we want. So we're ready to go. We're ready to set up our integral and try and solve this area. So we know that the formula for area, in this case, since our region has a curve that's traced out by y values butting up against the x-axis, we want the y values to be sort of essentially giving us our Riemann rectangles for our curve. So we'll want to use the first formula for area, which is y dx, the integral of y dx. And we'll go from t equals 0 to t equals 1. Now, of course, we'll need to work out what these are. So we know that our y, we already know, is given by the curve. It's y equals t minus t cubed. Now our x, we know, is 1 minus t squared. So dx, you can either say dx equals a function times dt, or you can say dx over dt is this derivative, and you'll just change the differential in the integral to a dt. I'd like to just say dx equals, same way we do for any kind of substitution, dx equals negative 2t dt, and we'll just fill that in. So we have the integral going from t equals 0 to t equals 1, we've determined those bounds, of our y, which is t minus t cubed, times our dx, which is negative 2t dt. Of course, do put the negative 2t in parentheses so that you don't accidentally think that you're subtracting instead of multiplying by a negative. So this is a very easy integral to solve. We just have an algebraic function in here. Let's just work it out. So this is the integral from 0 to 1 of, let's distribute our minus 2t. We'll have negative 2t squared plus 2t to the fourth, all in parentheses, times dt. And now we can actually evaluate the integral, get the antiderivative. This is going to be negative 2/3 t cubed plus 2/5 t to the fifth. And now we can plug in our bounds. So let's bring that over here. Of course, I should write our bounds first, 0 to 1. So we end up with negative 2/3 of 1 cubed plus 2/5 of 1 to the 5th minus, let's see, if I plug 0 into either of those terms, I'm going to get 0. So I may as well just write 0 right now instead of writing the terms individually. So 1 cubed is 1, so we have negative 2/3 plus, let's see, 1 to the 5th is 1, so plus 2/5. And we get, let's see, negative 2/3 plus 2/5, that works out to negative 4/15. Stop and think about that for a moment. Sometimes we solve integrals and we get negative answers, and we know that's okay. But here, we're interested in getting just an area, plain old area, and we're integrating a region that is above the x-axis. Our y values are always positive for the region that we're integrating. We've checked this. You can plug in values of t between 0 and 1 into the y function. You will see that you get a positive result. So why did we get a negative for our integral? That is very strange. That shouldn't happen in an area. Why is this negative? Now, I've warned you before, if you're solving an integral and you get a negative result where you expected a positive one, you shouldn't necessarily just swap the results to be positive and assume that that's correct. It might be correct. Sometimes it turns out to be correct. But sometimes it means you made some other more important, more fundamental mistake, and the actual answer will be something totally different. So you need to be very careful about this. Don't just merrily go along taking the absolute value and assuming that your answer is right, because it might not be. We should find out why we got a negative answer here and what's going on. And to answer that, let's go back and look at our graph. So here's the graph that we looked at here. And we worked out that in order to get the positive y values, the top half of that loop, we should let our t go from 0 to 1. But what's going on here is that we're starting, when t equals 0, we're starting on the right-hand side of the curve, and we're tracing out our curve going from right to left. So our y values are positive, but the change in our x is negative. Our x is decreasing as we move on. So y is positive in this region. But dx dt is negative. And since dx dt is part of our integral, that's why we're getting a negative result. It's because our integrand actually comes out negative, because you're taking the positive y times the negative dx. So there are two ways we could fix this. One way is we could just swap the bounds. We could say, well, when t equals 0 and then t goes up to 1, that's the sort of natural progression of values that makes t increase. But you are allowed to use bounds in an integral where the lower bound is actually higher than the upper bound. And you could force the issue by saying, I want t to start at 1 and go down to 0. And if I do that, I will force the x values to decrease and the dx dt to basically go down, because essentially the dt there is negative. And then the dx is also negative, and you multiply and you get a positive result. So you can force the integrand to become positive because you're actually integrating from left to right the way that we should, by forcing the t to start at 1 and go down to 0. Or the other option is you just acknowledge, okay, well, I'm integrating the correct region, and my dx dt is negative, which is why I'm getting a negative result, so I should just take the absolute value of the result, and that's the positive result that's correct. So the conclusion really is our result, if you just make our result positive, it will be correct. But let's do this slightly more carefully here. Let's go back to our work here, and let's say, okay, I need to switch my bounds here. I want to force the issue. I want to force the x to increase as we go along, move from left to right so that I have a positive integrand here by starting off with t equals 1 and then going up to t equals 0. So we'll change this. This will be 1 to 0. This is 1 to 0. This over here is 1 to 0. Very few changes here. I'm just swapping the bounds, that's all. And that means that I can get rid of all this stuff and replace it with, we'll just now plug in our bounds the way they should be. So we're going to have negative 2/3 of 0 cubed plus 2/5 of 0 to the 5th. Minus a negative, that's plus 2/3 times 1 cubed. And then minus a positive, that's negative 2/5 of 1 to the 5th. And that will give us positive 2/3 minus 2/5, which gives us positive 4/15. So now we have a positive result because we swapped our bounds. So for our final result, let's go back and look at our graph one more time. So for the total area, that's going to be the top area, the area of the top half of that curve, times 2. And our top area is 4/15. Multiplied by 2, that gives us 8/15. And that is the total area of this loop, the whole area of the whole thing. So there we go. 8/15 is our answer.